Okay, the final presentation of this session is entitled Pilot Scale Hydrothermal Treatment of Paper Sludge, Olive Pomace and Orange Peels into Intermediate Energy Carriers, presented by Dr. Douwe Zijlstra. Douwe obtained his PhD in Chemical Engineering at the University of Groningen and now works at TNO as a scientist focusing on hydrothermal upgrading of agricultural residue streams. Douwe.
Yes, welcome everyone, also for people online, and thank you for the nice introduction. Well, I mean, I'll already tell you that I don't have any fancy presentations or live streaming of processes going on, so I'll just keep to the results that we've obtained during the pilot, or at least the first parts of the F-Cube projects, where we first did some initial lab testing, and from there went to the long duration pilot testing on site. So yeah, the title has already been introduced. It's one of the longer titles of it. So it's where we test the three different streams: paper sludge, olive pomace, and orange peels on lab scale, and from there go to pilot testing. Well, to quickly introduce myself, yeah, I've joined TNO 2 years ago, basically in the transition stage, where like three of my former TNO colleagues went to the Torwash company, and I came into the TNO also to continue the Torwash work of TNO. Well, quickly about TNO, for the people who don't know TNO, it's an independent research institute from the Netherlands, which actually exists by law, just for independent research. It's almost 4,000 employees working at TNO, and the research is aimed at maximum impact on the bigger societal challenges that we face today. And the topics are very diverse. They range from energy and health, and also the defense, AI, lifestyle. So that's a very wide range of topics going on, and you can see that, well, I mean, it's mainly in the west of the Netherlands, but yeah, it's like on very multiple locations. Yeah, we TNO, for the work we process, we're from the bio-based circular technologies group, which is located in Petten. It's one of the more northern locations. It's a part of the energy and material transition cluster. And our group focuses on developing technologies for biomass upgrading, and it's like all hydrothermal treatments, and which range from relatively mild conditions for upgrading and a biorefinery up to higher thermal, higher temperature treatments like combustion and gasification. Yeah, myself, I'm more focused on the milder treatment, which is also the Torwash technology that's being developed. It's yeah, one of the milder treatment technologies that we have. The focus of this talk, because Heather already gave a bit of an overview of yeah, the entire F-Cube process, and this focus on this talk is really on the first part. So basically for the feedstock determination, the characteristics, then do some Torwash treatment, and part of the dewatering that's been done on site. So you obtain the press cake and the filtrate, and yeah, the use of the press cake and the filtrate that will be treated after lunch and for different topics. So the main focus is on the Torwash treatment. And then from there, it's like, yeah, it starts on lab scale experiments, and then we go to the continuous pilot scale. Well, first for hydrothermal treatment, I'll give some background just to explain what's going on in the process and why we use this technology for the different feedstocks. Well, if you go for a mild treatment, there are actually two main options. There's hydrothermal carbonization, which in our process, it's the variant of it's the Torwash technology, or use torrefaction. And the main difference, it's already been stated pretty clearly, is the use of water. And well, where the hydrothermal carbonization and also the Torwash process uses water as a solvent, and dry torrefaction, yeah, you don't use any solvent. And the use of water has quite some advantages. Well, you can use wet streams directly. That's already a big bonus, because you don't have this energy-intensive drying step beforehand. Yeah, the water catalyzes multiple reactions like the thermal decomposition, the hydrolysis reactions, in which you can obtain multiple projects, and you also have some chemical modifications in your product which are very favorable to use it as an energy source. And additionally, it removes the bulk of the minerals and the salts in the water phase, which for combustion is also very favorable. Torrefaction has a few advantages, but that's more, the main advantage is you can use a lower operational pressure, and it's a more mature technology, which is not necessarily a benefit, but it's more like, okay, that's the current status. And especially on continuous operation, torrefaction is easier, but as you have seen in the previous talk, there is already a demonstration scale going on, and also our pilot, it focuses on continuous treatment, which is, of course, the way to go if you want to go towards an industrial process. As I mentioned, upgrading of challenging feedstocks. Well, the 3 feedstocks has been named already a few times, and I think you'll hear them a few more times today. Like the orange peel, the paper sludge, and the olive pomace. The feedstocks, they have too much water to be typically treated as an energy source. And also there are many salts are present in these. So by a treatment, if you can remove also the bulk of these, it makes further processing much more significant. And the most important thing is, of course, to make these streams valuable. So the trick is to produce valuable products, which is for this project is fuel products, like the energy carriers and also the biogas production, and also preferably to co-recover valuable byproducts like nutrients present in any of the streams, to apply these relatively small streams, but which have a high value, to also implement these to have to further improve the business case. But I think that part will be mainly covered in other talks. I'll just quickly show what's happening. I mean, well, the colors are not very nice on this screen, but here you can see them much nicer in the process. I use the orange case because I mean that gives color-wise gives the biggest difference. Well, you just clearly what we use is like we have the milled orange peel, which is a bit diluted for the process, which is it looks like the very typical orange juice. After the process, you have this effluent that you obtain, the tar wash product, which is much darker. And if you look closely, at the top it's a bit light red, and at the bottom it's much darker. So you can already see the product, the solid is already settling a bit, which can be filtered off relatively easy. And then you obtain this filtrate, which is almost completely rid of solids. There's only like a very small amount left at the bottom. So this is obtained by the filter press, which shows that you can remove the solids relatively easy after the tar wash process, and to also obtain a relatively clear filtrate for which can be processed afterwards. Also we mentioned we use very dilute mixtures, especially the case for biosludge. Typically 1 to 4%. During our pilot testing, the feed was relatively, or even more dilute than normal. Normally, it's about 1.5 to close to 2% was the dry matter content, which you can also see on the picture on the left. It's this very nasty material, which is impossible to filter, because if you filter it, it gets out. You don't get a nice solid. But then after the tar wash treatment, you can filter it pretty well. And at applied pressure that we used, we managed to get a dry filter cake of approximately 40% dry matter, which is it's already a very nice solid material, and it's a very major improvement compared to this 1.5% starting material. And maybe if you recall from Heather's first talk, is that with the use of fiber sludge, which is now at the moment done in the process, they typically achieve somewhere around 30% dry matter after dewatering. So this clearly shows that by using the tar wash process, you already get a much better product, and you don't need to use this valuable material for the paper industry. So this clearly showcases that by using this hydrothermal treatment, you have a big improvement on the obtained product. Well, before we could start the pilot campaigning, we had a lot of screening going on. And the most important process parameter of this entire process is temperature, because it really affects many of the characteristics of your product. And yeah, I'll show them in the next 2 slides, just to have a bit of an idea what's going on. And also, well, these are the most chemical slides that I will show, so don't worry too much. The one on the left is this von Craven diagram, which most of you most likely have seen before. And this shows a bit, that shows the relation of the hydrogen to carbon ratio and the oxygen to carbon ratio of the feed. And on the top right, you see biomass, and then if you go more to the left, you see more the traditional energy, the biofuels like lignite, coal, and also peat, which have a lower oxygen to carbon ratio and also a lower hydrogen to carbon ratio, and which is typically related to a higher heating value of these products, and it's mainly because of the removal of the oxygen. And as you can see, like, well, I just took this one from a literature example, that like where the red dot is the initial residue, and then with treatment at different temperatures, you move more towards the traditional biofuels material. So then the oxygen to carbon ratio goes down, the same for the hydrogen to carbon ratio, and the higher heating value goes up. So this shows that higher processing temperature is in principle better for the properties as a fuel. But then there are also some other effects which favor lower temperatures, which for the most important one is, I think, the solid yield. Because the solid yield, as on the right picture shown in red, the mass yield of the obtained solid goes down with increasing temperature. Because yeah, you have different processes, and at higher temperature you also have a lot of liquefaction. So you dissolve many of your solids into the liquid phase. And yeah, and this loss of material is also seen like in the mass yield, but also in the energy yield of the product. So here, this is like a balance. You have to find the optimal temperature to have good properties, but also a good solid material. And some other effects is the dewaterability, which is already also very important for this process, because you have to be able to really press it and to remove the water. And here, this, for the dewaterability, higher temperature is favorable, because also the biomass becomes a bit more brittle. It becomes easier to compress. And if you process it at too low a temperature, it's not even pressable at all, so it's not dewaterable. So here you have some require some higher temperature. And then for the liquid phase, the digestate, if you go to high temperature, you can form phytotoxic components, so the digestion becomes not as optimal, but then if the pressure is low, you have not very high dissolved fraction, and then also the yield at that step is a bit lower, but the main part for the digestion is that you don't want to go too high in temperature. Then another important one is the removal of some key elements. Many of the heavy metals, they remain in a solid fraction, but there are also a few of the other elements that dissolve in the liquid fraction, of which the most important one are sodium, potassium, and chlorine. And in particular, the removal of chlorine and potassium is very favorable for a combustion, because chlorine is really corrosive, and potassium causes slacking in your reactor at the elevated temperature. So removing these elements is very beneficial. So, and this is also a very key improvement on the material that you obtain with the process. There it goes. Some lab scale preparations. Well, the goals of this pilot, the first thing that we did is like to determine the chemical and physical properties of the streams, determine the process conditions, and then also important is the de-risking of the pilot campaign. Here we have our material again. What we typically do is we start with some temperature screening. So with this multiclave setup in which you can very quickly screen multiple temperatures just to see the effect on the yield and the dewaterability, which is the very first rough quick step. Afterwards, we test the optimal temperature in autoclave to verify if it's also the correct temperature at a bigger scale. And then I think the most important step in the preparation is the pilot testing. And also for this one, you have some other constraints, because the pumpability of the mixture is a very important parameter. And for paper sludge, this is not really an issue. I mean, it's diluted enough, it's easy pumpable. But for olive pomace and orange peels, yeah, the moisture content or the dry matter content is about 20%. And in particular for orange peels, the pumpability was quite an issue. So we've done quite some testing to dilute it. Well, first we tried like 8 to 10%, and it worked, but it gave some problems with longer duration testing, like some issues with settling, some variability in heat, like heat transfer. But yeah, the optimal process condition, at least at the settings that we applied, was around 4 to 5%. You could go to optimal treatment. But yeah, and well, this knowledge we obtained with multiple pilot testing on location, still in the Netherlands. And well, this helped a lot for the pilot campaign, so because we didn't need to do this screening step and all the problems that involved by using too high concentration and required cleaning afterwards. So this made the pilot testing significantly easier. And then also in the lab testing, well, we did different, well, part of the analysis, of course, is how the waterability is, like pressing the small press cakes, the solids, and this liquid effluent, and then that can be analyzed afterwards, of course. And here I just show like a quick example of how this lab testing looks like for the biosludge and the mixed sludge. For the biosludge, this is the solid yield diagram. You can see that the yields going down over with temperature. And so here you can clearly see this effect. And there was also supposed to be at least a line showing the dewatability going up, but that one apparently fell off. But you can see the dewatability going up, and then for bios, and it's quite a sharp increase, because at 160, 170 degrees, 180 degrees, the dewatability was quite low, and then you have quite a big spike going up to around 50, 60% at 190 degrees, and then it remains quite constant at 200 to 210 degrees. So that made us choose the 190 degrees as the optimal process temperature. We did the same, well, we tested conditions on an autoclave for both biosludge and mixed sludge. And here the solid yield was actually a bit higher, but I think that's also because you use a bigger scale, so you have less loss in workup and stuff. So yeah, bigger scale allows for a more accurate mass balance. And then we test these conditions in a pilot scale, like 185, 195, 200 degrees. And then for biosludge, we notice that at 185, the material is not pressable. And then if you go up a bit to by 10 degrees, it's like only a marginal increase, like this 10 degrees. But then all of a sudden, the material is very well pressable. So there is a really small temperature difference that has a big effect on the dewatability. So it's a very, in that sense, the optimization is quite a tricky process step. And here you can also see that for the mixed sludge, the dewatability is a bit higher, but the fibers present actually caused problem in the reactor. So that's why the biosludge itself was actually easier treatable in the Torvos pilot, while it's actually considered usually the more problematic stream. So it really depends also on the technology, what's your problem. Then some pilot campaigning. Well, that's really to test the residue streams on location. And yeah, that's also a part of improving the TRL and obtain all the data that's required for any further analysis as well. And also we have for each working package, we had a few goals like requirements for operational hours and product and production. I think the operational hours were usually 200 hours of continuous operation and 100 kilograms of production. Well, this European tour was already shown by Heather. That we've been through a bigger part of Europe, and especially the container made quite some hours on truck. And yeah, this one is on site. Well, I can see a few more details. Like on the top of a container, you can see the feed. This is where we pump the diluted material. It goes to the Torvos reactor, which is not visible in this picture. It's in the containerized. And then on the bottom, you can see the product IBC, where we just obtain the product. and a sampling point for a quick analysis. Like usually on site, we do like 2 to 3 analysis a day just to see if the process is running well. Yeah, we did 3 campaigns, and yeah, the operational time for all of them was easily met. I mean, we had to go, like, I think for the biosludge we had to do 400 hours, and olive pomace and orange peel at least 200 hours. Well, we easily passed these hours. The goals for press cake production were 100 kilograms per stop, but yeah, we didn't obtain this goal for biosludge. But that was mainly caused by the very low dry matter content, because I think in initial planning it was assumed that the dry matter content would be around 4%. Yeah, we were working with 1.5%, so yeah, that difference can be easily explain why we didn't reach that target. But fortunately for all the other projects, we could reach the target, but for some of them we needed to do quite some operational hours, especially for orange peel. Because yeah, for all the pilot testing, yeah, of course, pilot testing, it's also the way to find out what's going wrong in the system or what can be improved. And for for all the different feeds, we had some problems. Because with olive pomace, it was milled, but then still there were these very small olive stones present, which settle quite rapidly in the reactor. And that over time gave also problems with, yeah, like with the flow profile and also a bit with the heating, because they get stuck on the bottom, so the heating becomes less optimal. So yeah, that requires some, some cleaning steps from time to time. I think like every 4 or 5 days we had to do a cleaning. So for this feedstock, yeah, you need to do a better pre-treatment in order to use it, like maybe like an important lesson. And for the orange peel, many of the solvents are actually soluble during the processing in the water phase. So the majority of your carbon actually dissolves. So yeah, the yield is relatively low for this feedstock, at least at applied temperature. And yeah, this also resulted in that we needed to operate for quite a long time in order to reach the press cake production. But then the properties of this press cake was very well. Like we had very nice pellets with very good combustion properties. So yeah, that's yeah, everything has its trade-off. We've noticed. And yeah, I can show some of the analysis, at least some data, but at least I'll first show the general trends, because I think, yeah, in the end it are just numbers which really depends on the feedstock. But the general trend is that the dry matter content goes up significantly, the ash content goes down, the carbon content goes up, the nitrogen and the hydrogen content are not that much affected in the process, the oxygen content goes down, and the higher heating value goes up. These are the general trends. Well, now just put it like a big table where all the results are a bit shown, but at least the general trends are true for all of the streams, that the dry matter content goes up, and particularly for the paper sludge, that's really significant. And also all the other trends hold true, except for the ash content in the paper sludge, which goes up. But yeah, the ash content was already very high at the start, and it's mainly heavy metals, as was Levine already told. Like that's one of the problems with the biosludge stream. Like it's a lot of metals in there, and these accumulate actually in the hydrochar, so or in the obtained press cake. So that makes it less suitable as a combustion pellet. But of course, there are other uses for these kind of chars as well. So maybe that's, well, I think it will be mentioned in one of the other talks. What are the optimal, or what uses are there for these feedstocks? And then also part of it is, or one of the few improvements are the reduction of in volume and the removal of moisture, because that's also for a transport point of view. And that's at the bottom. You can see that especially for the paper sludge, the moisture removal and volume reduction is huge. And yeah, for olive pomace and also orange peel, yeah, it's like still up in the 80 to 90% removal. So that's a very significant improvement. Yeah, this is like as a final slide just to show that not everything went well. We had some problems during the processing, like some charring of the olive stones, or at least from the olive peels that didn't go as planned. And also with the pressing at one of the first tries, you can see the different chambers. Like one was just still the sticky mess, but with all some process adjustment, we managed to overcome all these. But yeah, during these long hours, we've also had plenty of time to improve these. So yeah, that was all the things I wanted to tell you. So thank you, and if you have any questions.
Yes, any questions from the floor?
Yeah, thanks for your presentation. Yeah, I have, in one of your slides, you listed some advantages for hydrothermal carbonisation. So I just want to ask, do you have any ideas about the main minerals in the sludge? Because you mentioned that one of the advantages for hydrothermal carbonisation is removal of minerals and salts.
Sorry, salts, yeah?
Yeah, so the first question is, do you have any idea about the main minerals in the sludge?
Well, I think there was still some potassium that could be recovered, I think, but from the streams. Oh. Yeah, I think one of I think it's potassium was one of the key elements that could be recovered from them, but I'm not 100% sure. But I think it's one in the upcoming talks for sure that at least that discusses this part of all these elements that could be recovered. But from the sludges, I think, yeah, it's mainly rich in heavy metal, so it's not the most convenient. But yeah, or I can also look it up. But I think it's also discussed like in this MPK recovery in one of the upcoming talks, like how this can be recovered from the streams.
Okay. So the second question is, how do you achieve the removal of minerals from the sludge by using the hydrothermal carbonisation process?
Yeah, I think there are many different processes going on. So basically, you first really disrupt the biomass structure. So with hydrolysis, you remove the hemicellulose, so the cellulose and the lignin part. It all becomes much more accessible by the water. And basically, I think this makes it much easier also to flush out the water through the entire biomass, so that it makes it much easier for all the elements to dissolve in the liquid stream, and by that way remove most of the some of these nutrients. I think that's the main part, because you need a certain temperature in order to get to achieve this goal, and that's really at the temperature where all this degradation, the first degradation reactions occur in the biomass.
All right, thanks.
Okay, thank you. We have a question online very quickly. So the question is, what are the pre-treatment steps that you need for olive pomace?
Let's see, I think what we did was like a sieving step, or at least some milling step. And at first, when we used the pomace directly as obtained from the site, it gave some more problems. So there was a milling step, and we did some sieving to get the more finer particles, because that made at least the degradation more easier. Because I mean, if you had too big particles, the degradation step becomes slower. And I think, there you have, of course, the problem also because you want a certain residence time. So I think then at first the residence time wasn't long enough. So you need, to break down the particles, to mill them or grind them into smaller particles. And at some point we did a sieving step to remove the bulk of the olive stones, which was quite a labor intensive, but then in the same time it didn't require this maintenance steps every few days. So it was a trade-off. So that was one of the things that we noticed, that particle size is a very important parameter of the feed. And
the feedstock required dilution, correct?
Yeah, because I mean that was also an important one, because I think it was roughly 20% dry matter content, and we diluted it to 4% at the start, and in the end I think we went as high as 6 to 7%, and it didn't give any problems, at least. So maybe that could also be because we used more finer particles, that we could go a bit higher concentration. But we didn't really have the time to really see that relation, but at least we could go a bit higher in concentration for olive pomace, and I think that's an important further step, because if the dilution is not, of course, not preferred. I mean, you want to use the high dry matter content as possible, of course, from an economic point of view, of course.
And sorry, just as a follow-up question, the question is, olive pomace has a high water content. Is sieving and grinding possible? Impossible.
Sorry?
Olive pomace has a high water content. Is sieving and grinding even possible? Is it effective? You found it?
Yeah, it is. Yeah, I mean, yeah, you can do wet grinding, wet shredding, stuff like that. That are techniques that are possible, and sieving is always an option. I think that yeah.
Tried and tested technique. Okay, thank you.